Hi folks, welcome back. So reinforcement learning has had some of the largest signature achievements in AI going way back to systems like AlphaGo. But then with large language models, mostly the focus was on supervised fine-tuning (SFT). However, with the recent release of all these reasoning models like O1 and DeepSeek R1, reinforcement learning is coming back, especially the variant that uses verifiable rewards, reinforcement learning from verifiable rewards. At a really high level, reinforcement learning is the idea that you want to train a model acting in some environment to maximize a reward function via trial and error. And the VR, the verifiable rewards variant of it, means that this reward function is an objective function, things like a unit test passing or failing, or a math theorem being checked as true or false. And so obviously RLVR is really applicable to these objectively verifiable domains like software and math. And this paper today looks at how to apply RLVR to agentic settings that go over multiple steps, not just one-shot calls to a model. RLVR has had lots of success with reasoning models, but it hasn't quite yet worked in agentic settings. And by agentic settings, they mostly mean something that requires reasoning over multiple turns and acting in a very complex environment, like say a software development environment. Why is that though? There's several reasons RLVR has challenges in agentic settings. The first one is simply the complexity of the environment. If you look at, for example, a software development environment and carrying out multiple steps in that environment, it takes a lot of infrastructure and compute to do that. The second problem is that you have multiple turns, and through each of those turns, the model is interacting with the environment and carrying out some reasonably complex step, and then the complexity increases even more if you chain together all those multiple steps. And this gets back to the fundamental problem of sparse rewards in these multi-step environments. What is meant by sparse rewards is this idea that when you're taking multiple steps towards some goal, say implementing a feature in code, the reward only comes all the way at the end of those multiple steps when you have a unit test passing or failing. And so while you're going through those multiple steps, while the model or the agent is going through those multiple steps, it doesn't know in the moment whether it's on the right track or not. For example, if it were going through a maze as an analogy, it wouldn't have any notion of whether it's getting hotter or colder getting towards the goal in the maze. And that is the main problem the authors are addressing in this paper. And the way they do that is by this notion of agent guidance. It's very much modeled on how a teacher teaches a student, how a human teacher would teach a human student, which is to say that as the student is making progress through a problem, carrying out multiple steps, the teacher gives guidance to the student at every step, either giving the student feedback on each step, telling them whether it's correct or not, whether they're getting closer to the solution, and so on. And they are applying that same idea of providing guidance at every step to agents learning with RLVR. So this diagram in the paper describes the overall flow. So step one is the agent attempts the problem with no guidance. And at the end of it, you get some notion of whether it was correct or not. However, if it wasn't correct, they then have this notion of a guidance providing model, a guidance model, which looks at the trajectory, the trace of steps that the agent took and provides feedback or guidance. And they have three types of guidance that can be provided to the agent. The first one is a plan. So this guidance model could tell the agent you should have followed this plan instead of what you did. The second type of feedback is environmental feedback. So these are hints about how to understand or interact with the environment that the task is happening within. So if this was a software development task, it would be hints about the libraries to use or the way a certain library should be used, or maybe how to configure it correctly and so on. And then the third category of feedback is how to interact with the resources in the environment. And this can get really granular. This can consist of hints like you should look at this file, or you should look at these sets of files within these folders, or this method within a file. So this is granular feedback about the contents within an environment. The authors have tried out an implementation of this idea for the software engineering domain. They've taken a bunch of software engineering tasks and performed this agent RLVR loop on these tasks. And the tasks are similar to what you would see in something like Swebench. They have a GitHub issue description from real world open source projects. Sometimes they will have error messages, expected behavior, and so on within this issue description. And the task is to fix this issue. These are all Python code bases. They are Dockerized, so you have a full development environment inside a Docker container. And that's the environment that the agent, the software development agent, is running inside. And the validation mechanism is, as you would expect, unit tests for the software project. Now, the central idea of this whole setup is this notion of providing guidance on a multi-step trajectory that the agent took. And the input to this guidance agent is all this metadata about the problem description, as well as the full trajectory, as well as the feedback produced in the environment in the process of taking all those steps. And here's the important part. In this setup, the guidance came from another more powerful model, Claude 3.7 Sonnet. But you can imagine that in other setups, this guidance could have come from humans as well. And the final data set had 817 sweet tasks. They got about 8,000 trajectories in all, of which about half were successful trajectories. And they performed this on a smaller base model. So they used Claude 3.7, a much larger model, as the guidance provider model. The base model that they were training was a 72B Qwen 2.5 instruct model. And with RLVR, its performance on these software tasks went from 9.4% to 22.4%. So that's a pretty sizable jump. And if you look at this graph where it compares pass at K, which is after K attempts, is the task successfully completed or not. And you can see throughout the range of increasing K, the success rate is noticeably higher with guidance than without. And in the appendix to the paper, they have the guidance generation prompt that they use with Claude. You are an expert software engineer generating helpful hints for debugging and fixing issues. And then they say the hint should be in the following format. And these are the three types of feedback or guidance that we looked at. It's either a plan or something about the environment, or something about the files or locations within files that need to be looked at. All right, so that was a quick look at how to apply the notion of RLVR, reinforcement learning from verifiable rewards, to the notion of multi-step agentic workflows, with guidance being a central idea. I hope you enjoyed that. If you like content like this, please like the video, consider subscribing, and I will see you next time. Thank you very much.